11. 7. 9. 6. 10. 10. You might expect that the most probable result would be 8, corresponding to half black and half white, but we get considerable fluctuation from them. 6. Well, we'll have to do this a large number of times in order to get a proper frequency distribution.
I don't think I have the strength.
Well, don't worry about that, because for this machine, I can calculate the frequency distribution. I'll show you. When I spin one of these cards around, it comes out either black or white, and I can't predict which. I can't see any reason why it should come up white instead of black. So first of all, I assume that these two alternatives are equally probable. Now, these squares spin quite independently of each other, so the final result is the overall effect of 16 independent random events. How do I calculate the probabilities of the 17 different possible results? There's only one way to get all black or all white, so these two meter readings are equally probable. And they're certainly not very probable. But look at the arrangement of squares right now. The probability of this particular arrangement is exactly the same as that for all black or all white. But the meter reads the overall effect and can't tell the difference between this arrangement and any other with 10 white and 6 black. So the probability of a particular meter reading depends on the number of different ways the reading can be produced. There are 16 different ways of getting one white or one black. So these two meter readings are equally probable and 16 times more probable than this. You may be able to go on now and calculate how many different ways there are of getting 2 white or 2 black. There are 120 different ways. Now, I'm already off scale here, but I plotted this frequency distribution before, and here it is, to a much reduced scale. You can see that the ones that I was calculating before hardly show here at all, and that the 8 is the most probable. Perhaps you can try working this out for yourself. But you must remember that when you do make a calculation of this sort, that you should do experiments to check it. Now, over here, I have a similar machine with spinning squares. Here, there are 256 cards in the same area. The overall effect of this one is made up of a much larger number of independent random events. What about a frequency distribution for it? For 16 cards, a reading of 8 is more probable than the others. For 256 cards, a reading of 8 is very much more probable than any other reading. In fact, it is so much so that I can almost say with certainty what the result will be when I spin the cards. I predict a reading of 8. Let's try it. again. The fluctuations are very much smaller here. This reading is predictable. That's why we said in the beginning that the overall effect of a large number of random events is very predictable. Now, at last, we're in a better position to talk about this law of radioactive decay that we started with. First of all, what does it mean to talk about activity? It should mean that a sample of radioactive material has a definite, predictable number of disintegrations in a certain length of time.
How can Dr. Hume speak of a predictable number of disintegrations in a certain length of time when the disintegrations are random? I'll show you with this. It's a Geiger counter which displays the number of counts here. I'll start it. 1, 2, 3, 4, 5. As you can see, the time between counts is not predictable. When there are 10 counts, then a 1 comes up in the tens column and the unit column starts over. Now I'm going to move the radioactive polonium here closer to the detector. This will increase the number of counts. The unit column is still random, but much faster than before. The tens column is pretty random, but watch the hundreds column. 600, 700, 800, 900. These are quite regular. There is some fluctuation. This fluctuation would be even smaller if I took 1,000 counts at a time. This is just the law of large numbers. I can never say what the time interval between single counts will be, but I can say fairly accurately what the time interval for a large number of counts will be.
Well, that's how we get the activity to plot on this graph. Now, why does the activity decrease in this particular way for all radioactive substances? This, too, fits the idea that disintegrations are random events. Perhaps I can simulate this behavior with a sort of game. Here are 60 dice. Think of them as atoms, a rather small sample compared to the vast numbers of atoms in any piece of radioactive material. Suppose that the 5s represent atoms that have just disintegrated. I'll pile them up here. The chance of a 5 turning up is just the same as any other number. It happens at random and is independent of what comes up on any of the other dice. These represent the activity in the time interval of the first throw. They are no longer the same atoms they were before they disintegrated, so that they are eliminated from now on. Now I'll throw again. The chance of any one of these dice coming up 5 is exactly the same as it was on the last throw. I'm piling these up beside the first row. This time there are fewer atoms disintegrating. There's one more. Now, I'm going to go on doing this throw after throw, and you'll see what I get. Next row. I still have a few dice left that I'm trying to get 5s with, but I'll stop here. This is an activity time graph for this dice game. And I want you to compare it with the activity graph for a radioactive substance. The dice graph isn't smooth. There are sizable fluctuations which are bound to occur because I had only a small number of dice. But the general trend is exactly the same for both. So it looks as if the law of radioactive disintegration is the same as the law of chance for these dice. I mentioned the law of chance for the dice, but I'd better say it again. The chance of any one of the dice turning out 5 is exactly the same on every throw. This means that the chance of an atom exploding in any one time interval is the same as in any other. It doesn't change whatever as time goes on. Atoms, unlike people, do not have a greater chance of disintegrating as they get older. The chance always stays the same. Perhaps you can calculate for yourself what the half-life of these dice should be. From this experiment, it looks as though it is about 4 throws.
So far, we've used one particular natural phenomenon, radioactivity, to illustrate random events. That's because the random nature of the individual disintegrations is apparent. Orderly behavior is observed for a radioactive substance only if the time for a large number of counts is used as a measure of activity. Now, you observe orderly behavior in the measurements that you make. For instance, you measure light intensity with a light meter. The needle doesn't jump around in an unpredictable way. Does the orderly behavior that you observe always arise because of random events? This question can only be answered by doing experiments, many experiments. These show that sometimes the order that we observe does have at the roots randomness which is not apparent. But this isn't always true. Sometimes experimental results indicate some sort of order at the roots.
How can we tell when randomness underlies orderly behavior? Here is orderly behavior. Every time these squares spun around, the reading was 8. It's clear that the order here comes from randomness, but I could not tell by watching the meter alone that this was true. Now suppose that I masked off all of the squares here except 16. The light going to the meter would decrease, and I'd have to use a more sensitive meter. But the point of this is that I could then tell by